Alrighty, welcome everybody. My name is Jacob Moss, and I'm here today with Ella Jones and Milo Johnson, and this is going to be our Physics 213 project number 2. The subject at hand here today is vacuum tubes, so we're going to be going over all that. Before we get started on anything too interesting, I'm going to be going over all the building blocks necessary to be able to understand and follow the following overarching explanation that'll be coming up shortly. Just to do so, I'm just going to be going over the basic concepts, some important terms, and just kind of showing you what some basic versions of this system looks like. So I'll just start off with a basic definition of what is a vacuum tube. It's essentially just a glass electron tube containing a near vacuum, allowing for the free passage of electrons. The first versions of these tubes were made in the early 1900s by a man by the name of John Fleming. He used concepts discovered by Edison in order to create a non-mechanical switch controlled by only voltage. Going off of that, the most important piece of knowledge floating around all this is known as the Edison effect, or thermionic emission, and it's essentially just the emission of electrons via the heating of a metal filament, typically tungsten or something along those lines, something coated in tungsten at least, to the point of getting so hot that it loses electrons. This point threshold is normally around 1,000 degrees Kelvin, something along those lines. And this was discovered from the most basic application, the incandescent light bulb, when it was found that it emits electrons when the filament was heated up enough. And then eventually we were able to translate this information over to a circle application, and that's where we were able to come up with the diode. So this is the most simple form of a tube, and it's made up of only two main pieces called the cathode and the anode. Diode just means di is two, ode stands for electrode, kind of gives you a basis of ideas what all the names of these are. Before I go too into the detail on this little guy over here on the left, I'm just going to give you definitions of all the main pieces of the puzzle down here on the bottom left. Starting off with the filament, probably the most important part of everything here. It just has the job of being a coil that you run a voltage across in order to heat it up to a set temperature. This set temperature is going to be where thermionic emission is capable of taking place, given the circumstances, what kind of metal we're using, and it's located relatively near to the cathode in order to be able to emit that heat onto there. Now this cathode is just a small plate. It gets warmed by the filament, and it's capable of beginning to emit these electrons. Now above that, we're going to have something called an anode. This just has the job of receiving these electrons. It's just another plate located a distance away, and typically contains a positive charge in order to facilitate the flow of these electrons across the space between the cathode and anode. Another important piece that is in the most common form of these vacuum tubes is called the grid. This is what gives us a lot of control. So in most applications, it's just going to be able to control the electron flow via a voltage across itself, which allows for the switch functionality that I was talking about earlier, being able to be a switch with no mechanical analog. And then last but not least, the vacuum in the tube is just necessary to permit the free flow of electrons, nothing getting in the way in there. So with all that in hand, I'll skip over the diode just for sake of simplicity. The triode is going to be essentially the same exact application, just with that grid in the middle. You can imagine what the lack of a grid would be in this scenario. So starting at the bottom here, we have our filament. This is going to be heating the cathode directly above it. We're just going to run any given voltage across that, whatever it needs to be. So as this cathode is heated, we're going to see some electrons start to disperse from it. Now these electrons, what they're going to want to do is they're going to want to head up towards this anode in this direction, just flowing wherever the free space is. So as they're going to do that, they're going to come across this grid, which is just a little cute wavy wire in the middle of this vacuum tube here. This grid is typically going to have a voltage across it, positive or negative, depending on the scenario that we're working with. I'll touch on that more here in a second. Let's say, for an example here, we're hooked up to a circuit, and for the circuit, we don't want any current to flow to it yet. So by applying a negative voltage across this grid, these negative electrons are going to reach this grid, and due to some properties that we're familiar with in this class already, they're going to reach this grid and turn around, because like charges like to repel each other. Now let's say we change our mind and we want some current to flow to this grid. By adding a positive voltage slowly to this, we can slowly allow more and more electrons to flow through towards the anode, allowing the circuit to complete itself. The more positive these charges are going to be, the more current you're going to see flowing, and vice versa. Last but not least, after we make it past that grid, we're going to be getting up to the anode, where these positive charges are going to allow for the electrons to flow through it into the circuit and allowing us to complete the circuit, getting power to wherever we need to. With all those concepts in mind, I'll be turning it over to Milo, who's going to be going over the explanation portion of the presentation.
All right. Now that we have the basics of the operation of how these vacuum tubes operate, we can then apply them to circuitry and see how they behave with exterior voltages, loads, and other circuit components. Now consider the following simplified circuit. We have a positive to negative voltage source across some resistor load, and we have our diode, vacuum tube, circuit component in this circuit. Now it's worthy to take note that the filament has a different voltage supply across it than the voltage source that is going into the main circuit components, which will apply to our diode. Now, when a negative voltage is supplied to this cathode, and this is heated up to some temperature from some constant voltage source, we can expect some thermionic emission and the flow of electrons from this negative source to this positive source at the top here due to this difference in voltage. Now, when we flip this voltage source, and instead make this positive and make this negative, a unique situation occurs. So this heated part, or this heated tungsten filament on top of here, now has a positive voltage as opposed to a negative voltage. Well, what does this mean? If this is negatively charged, we would expect the electrons to be emitted from this side and flow to this side, but that's not the case. Because this side is not heated as opposed to this side, no thermionic emission will occur, and no circuit will be completed by the flow of electrons across this vacuum gap. And as a result, we now have a one-way circuit direction, which then creates the diode, which we represent with this symbol. So imagine that current, or the flow of current, is only able to flow in this direction, but not in this direction, because of this circumstance that created across it. Of course, modern diodes are different from this sense, but this gives us the general idea of how a diode operates and how it was first implemented in early circuitry. Now that we've come to define the unique nature of vacuum tubes stopping current flowing in one direction or the other with respect to some larger circuit and the input voltage or current across it, we can use these diodes, or these one-way current operators, in larger circuit constructions to allow us to do pretty unique things with respect to some input voltage or current incident upon a resistor or diode configuration. So what I have here is a voltage source, an AC voltage source, meaning that the direction of the voltage is flipping with respect to time. For this purposes, we will say it is a sinusoidal input voltage with respect to time incident upon our larger circuit. Now, notice this very peculiar diamond diode configuration in the center of our circuit. I'll get to why it's constructed in such a way, but for now it will have a large effect on the direction of current flow throughout the circuit, which we'll track. So what we're interested in is in the direction that the current flows across this resistor, and for our purposes we'll just say that this has a positive side up here and a negative side down here. Resistors don't really have a voltage direction, but will allow us to basically induce a voltage on it in some direction, positive or negative, with respect to some input current across the resistor. Also take note that there is a wire bridge here, meaning that the wire that is coming down here is going over this wire here, meaning they do not touch, and that will be important when we're tracking our current direction across this circuit. So let us start with when the voltage across this AC sinusoid input is in a positive direction with respect to the circuit. Let us track the current through this circuit, starting by coming from the top of this AC voltage source, coming down into the top of our diamond. Note that via the junction rule, we should expect that some of the current to go in this direction and some of it to go in this direction. But because this diode here is stopping the flow of current in that direction, the current only has one option and will thus follow this direction. We now have another junction here, and now we can see that the current cannot go in this direction via the direction of this diode, and thus must flow across our load. We then can take note that in the green section of our sinusoid, across our load, we can expect a positive voltage due to the direction of the current coming in that positive side of our resistor in this instance. We can then complete the circuit to go back into our AC voltage source, noticing that we're going across this bridge that is not touching this bottom wire. We'll go back into our diamond configuration. Now the current can go through this diode facing this direction, but because it wants to go back into our voltage source after dropping a voltage across this resistor, we then notice that it will go across this diode and will flow back into the bottom side of our AC load voltage, which completes our circuit. Now, let us track the direction of our red side, where now the positive side of this input voltage is facing down. So we'll track the current, again going under that bridge there, not allowing the circuit to be completed. Will then flow up into this junction. Now again, we can notice that the diode restricts the direction of current in this direction and will only allow it to flow in this direction where the diode is facing the proper current direction we're interested in. We'll flow into this next junction here, where we can again see that the current direction is blocked by going in this direction and easily back into our voltage source, and thus must flow across our resistor. We can track this current into the resistor, and notice that it's coming into our positive side and inducing a positive voltage across this resistor. Now this is peculiar. We can track the rest of our current through this circuit, going back over this bridge across wires that are not touching. We'll go back into our diamond once more. Notice that we are able to go in this direction because our current wants to complete its circuit with respect to the input voltage. It will flow across this resistor instead, back through the top of our diamond, and back into the voltage source, completing the circuit on this side of the sinusoid. Now notice that even though this sinusoid is changing voltage and inducing different directional currents across the input, our diamond diode configuration makes the output voltage across this load in the same direction, meaning that even though the input voltage is changing and making the current across our input in multi-directions, the current across the load is always going to be in the same direction because of this stopping of current in one direction with respect to another. We call this configuration a rectifier, meaning it rectifies the AC voltage to be in some other configuration with respect to an output load. Now considering the following circuit consisting of a triode. Here we have an antenna that's connected to our grid, so imagine that as radio waves come in here, such as in a radio, a small positive or voltage change will exist across this grid, sort of something like this, or maybe some like noise in between, but nonetheless it'll be very small. Now, if we try and hook this antenna into our circuit just directly, the noise across our speakers would be very, very low because the voltage across it is very small. What we want to do is amplify it, and vacuum tubes allow us to do this. So take note that the distance between this grid and this cathode is much closer to this negative side of our current, which is going to be doing the thermionic emission, emitting those electrons across that vacuum space. Now, even if the voltage across this is very small compared to maybe this voltage up here, it will have dramatic effects on the flow of electrons through the circuit due to its proximity to the cathode and those negative electron charges. What this means is that if our circuit stays constant, we apply that constant current across our thermionic emitter, what we'll see is, like, with these very small changes as an input from this antenna, we can expect larger flow of electrons, smaller flow of electrons, larger flow of electrons, so that the ultimate noise or AC voltage that we experience across this load will be a much, much larger voltage difference in response to the small input voltage across this. In essence, we have created an amplifier, or what later would become known as a transistor in circuits. Basically, the flow of current into it basically acts as a control or dial for the voltage and current across our circuit. I ask you to now consider the following circuit with a triode in series with another triode, a voltage battery source, and a resistor in a larger circuit configuration. Now, the reason I have three inputs here is one of them is connected to the cathode of our circuit and the other is connected to the anode of our circuit, and then a third source is going into our grid in between those two sources. Notice that in each of these configurations there's a ground source here connected to the positive side of the battery and then the negative going into our grid. Notice that when this switch is then closed, a negative voltage difference or collection of negative charges now exists across our grid. So when both of these switches are closed for each of these vacuum tube triodes, basically the voltage difference on this grid in each of those diodes is a negative voltage. So then when the original circuit is then run, we can expect that from this negative cathode source, electrons will be emitted via thermionic emission, but because a negative voltage source exists across this grid, and with the idea that like charges repel one another, the negative electrons will be redirected. And no circuitry or current will be allowed to flow through the larger circuit components. So essentially acting as a voltage switch in our larger circuit. Now, when we open one of these, like so, then our voltage across our grid is now nullified, and no voltage exists across it. Thus, we have a normal diode in our configuration, and current is allowed to flow via the thermionic emission of electrons from our cathode to our anode. However, because this lower diode is not allowed to flow, or the negative voltage is induced across our triode configuration, then the current through the larger circuit will again not be allowed to flow. However, when we then open this circuit, then and only then does current allow to be flowed through our larger circuit and through our load resistor. Now, this very idea of using voltages to stop the flow of voltage through a larger circuit configuration is what we call an AND gate in computational and algorithmic software, where if one input source has a voltage across it but the other doesn't, then no voltage is allowed to flow through our AND gate. These logic gates can then be configured together to form AND, OR, XOR, NAND, NOR, NOT, and other forms of logic gates that use different but similar configurations of triode or transistor-like elements that use voltage to stop the flow of voltage in other circuitry.
Hey y'all, my name's Ella and I'll be doing the sense making section. So a big part of our sense making section is going to be Maxwell's equations because these four equations are a huge part of the vacuum tube. So these are your four essential, which we've actually learned a few just in different terms. These are just more complicated. A few definitions just for the variables. This J vector is going to be the current density, and the rho, as we've seen before, is going to be charge density, which these will come into play later on. So out of these four, there are two that are going to be changed based on what medium, what is going on, and two that aren't. So the two that aren't are going to be these middle two, which are the Gauss's law for magnetism and Faraday's law of induction. These, same, we don't bother with those at the moment. These two, however, because of certain variables that they have, which are defined below, are going to be different. So, with the charge density and the current density, there is no charge ions, therefore there is no flow of current. Because of that, this P right here is going to equal 0. So, cancel it out at 0, and obviously it's just going to be 0, so you're going to have, it's going to equal 0. The next change is going to be with Ampere's law, the modified version. This J vector, since there's no flowing current, is going to equal 0, so it's going to completely cancel out this first term right here, which is just going to leave the gradient crossed with the magnetic field is going to equal this right here. So all of this really does make it possible, triodes, diodes, for all of this, the open switch. So this vacuum tube is basically going to act like an open switch since there's no current flowing, which is why diodes and triodes and things like this exist. I believe ENIAC computer, which is consisted of 18,000 vacuum tubes. because of these vacuum tubes, that is why we have computers, we have the ENIAC, it moved on to transistors, and then after the transistors, there was integrated circuits, and so on, which is insane to think about that all of this innovation and advancements in technology have to do with physics. For our reflection on basically how we've learned all of this and what it applies to, the main thing that we wanted to take away from this was the electric controlled switches, which is basically canceling out electricity with electricity, as well as inductors and capacitors. And those two things, especially with doing them separately, learning about parallel plates and solenoids and all of that, and then applying it to circuitry, as well as just every other circuit element we've learned in this course. The innovation of electric switches, as well as that just directly translates to transistors, computers, integrated circuits, and then what also links to that is the logic gates, which was discussed in our explanation task, which is why you're able to watch this video.